Hello everyone, I'm your academic coach Yuhyun. I'm a UCLA grad, a professional tutor, and a digital creator. I post videos on YouTube and live stream on a regular basis to provide free educational contents. If you find my videos helpful, please subscribe to my channel, like my videos, and leave me a review on Google. Let's get started. So today I'm going to talk about Unit 1 of AP Physics 1 Kinematics. Kinematics is the most fundamental and then one of the most important part when it comes to mechanics. In kinematics, we study how an object moves, but we're not going to study why an object moves in such a way. We're only going to focus on how it moves, including in which direction it moves, moving upward, moving down, or moving to the left, moving to the right. Is it doing a linear motion or projectile motion? Is it speeding up or slowing down? Is it accelerating or decelerating? Is it changing a direction, etc.? So I'm going to start with the most important concepts in kinematics, which is displacement, velocity, and acceleration. Remember that all of these three concepts are vector quantity rather than scalar quantity, which means they always come with a direction. Both magnitude and direction are important in the vector quantity. So displacement, how it is different from distance is that distance takes all of the routes that you have passed, that you have traveled, while displacement only cares about the initial position and the final position. So displacement is literally just change in the position. And a lot of times it's represented as delta x, which is x final minus x initial. You can replace x with y if it's moving up and down in vertical motion. And when it comes to distance, you will have to take every single part of the path you took. So let's say you move between point A and B. So let's say you're moving between point A and point B, and then they are 100 meters apart. Then when you go directly from A to B, the displacement is 100 meters and distance is 100 meter as well. But if you go from point A to, let's say, point C and then going back to point B, then your displacement is still 100 meters while your distance is more than 100 meters, probably 150 or 200 meters. So distance is not always the same as displacement. Or let's say when you move between A and B, you went to B and then you're back to A. Then your distance is 200 meters, 100 meters from A to B, another 100 meters from B to A, 200 meters in total. But your displacement is 0 because your initial position and final position are the same. There is no change in the position. So again, displacement has nothing to do with the route you take. You can take whatever that you route take, and then when you're back to A, your displacement is always 0, while distance is not. And in physics, we always use displacement to calculate all the information you want rather than the distance. Now I can try to compare velocity to speed, just like I compared the displacement to the distance. The velocity is the vector quantity, while the speed is the scalar quantity. And how I calculate the velocity is, it is the instantaneous rate of change in the displacement. So a lot of times when we calculate the speed, what we do is we take the total distance and then divide it using the total amount of time it takes. So we calculate the average speed. So that's not what we do in velocity in AP Physics 1. So we usually only talk about the instantaneous rate rather than the average rate. So how you're going to calculate the velocity is by taking the change in the distance or by taking the change in the displacement and divided by the amount of time it takes to travel the amount of the displacement. And later, I will talk about how to calculate the velocity or how to find the velocity on the position versus time graph. And next is acceleration. So acceleration tells us how fast a velocity is changing. So velocity is not always constant. An object might speed up or slow down. Its velocity is constantly changing most of the times in real world. So acceleration tells us about how fast the velocity is changing. So, for example, for a sports car versus a regular sedan, so sports car has a very high acceleration, means within 1 second, its speed can increase by a large amount. So that's why it has a lot of advantage when you just start in a race. On the other hand, for the sedan, even though it can still reach the high speed of, let's say, 100 meters, 100 miles per hour, but at the very beginning, it's accelerating slower. So for every second, its speed is not going to increase that much. So that's when we compare the acceleration, the rate of change in the velocity. And then we always use delta v, the change in velocity, divided by time to represent acceleration. And again, acceleration is also a vector quantity. So in AP Physics 1, we always relate displacement, velocity, and acceleration all together. Okay, and now let's talk about how to analyze the graph of the velocity versus time, and then how to analyze the graph of the displacement versus time. So when you see a graph like this, it means that its displacement or the position is constantly changing. So it is a curved line. It does not mean that the object is moving along this curved line. It just means that its position is changing along this curved line as the time changes. So most likely this is a one-dimensional motion or a linear motion. So this object must be moving along a linear line. It can be a horizontal line, it can be a vertical line, it can even be a scanted line. And on the linear line, you usually set up the positive direction and then the negative direction. And usually I set the right side as the right as the positive and left as the negative. And its position is equal to 0, which means at the very beginning it starts at the position of 0, and then after 1 second it has moved to this position. After another second it has moved to this one. After another second it has moved to here. After another second it has moved to there. Okay, so it represents the motion of this object along this linear line. And this is the vector diagram. The direction of the arrow represents the direction of the velocity, the direction of the motion, and then the length of the arrow represents how fast it is moving, the magnitude of the velocity. Okay, and based on the position versus time graph, how I draw the velocity versus time graph is by taking the slope of the tangent line. Okay, so the slope of the tangent line at a specific point, let's say at time t is equal to 3 seconds. So how I find the velocity is by drawing a tangent line to this position versus time graph at a specific point, and then calculate its slope. So this slope represents the velocity. And it's obvious the velocity when time t is equal to 0 is 0 because it has a horizontal tangent line at time t is equal to 0. And then the tangent line gradually is tilted up, which means the velocity is gradually increasing. So based on this position versus time graph, I can come up with a velocity versus. And the velocity versus time graph, on this velocity versus time graph, velocity must be increasing from 0. And on this velocity versus time graph, I can also find the acceleration by taking the slope of this velocity versus time graph line. So the slope of this linear line is the acceleration. And since this is a linear line, its acceleration is always constant from the very beginning to the end, which means it's a constant acceleration motion. So in AP Physics 1, you will rarely see the scenario of a changing acceleration. Usually we assume that acceleration is constant to make sure that calculation is a little bit easier. So on this velocity versus time graph, the area of this triangle represents the change in the position or displacement. So similarly, based on this velocity versus time graph, I can also draw a acceleration versus time graph. And since acceleration is constant, acceleration graph is just a horizontal line. And this horizontal line is above x-axis because it is a positive slope. And again, the area under the acceleration graph represents the change in the velocity. Now I'm going to give you a couple of examples of the linear motion in real world. So one of the most common linear motion with a constant acceleration is free fall. So free fall means an object is moving in air under the influence of the gravitational force only. So it only experiences an acceleration that is pointing downward. So gravitational acceleration means it's a 9.8 meters per second squared downward acceleration. So let's say if I hold an object and then release my hands, it just drops. And once it drops, its velocity increases downward. So right at the moment when I release it, its velocity is equal to 0. And then because it's experiencing gravitational acceleration, so its velocity increases. And then its velocity increases by 9 meters per second. Sometimes we use negative 9.8 meters per second per second squared to represent the gravitational acceleration. This is because I set upward the vertical upward as a positive direction and then downward as negative direction. But I can always set the direction arbitrarily. So sometimes we can just set downward as positive direction to make the calculation a little bit easier. What happens if I toss an object upward? Okay. So if I toss an object upwards, then it has a non-zero upward initial velocity. So it has upward initial velocity, and then its velocity decreases because of the downward acceleration. And then at the maximum point, it's temporarily at stop. It's temporarily at rest, and then it starts to move downward. Again, due to the downward gravitational acceleration. So on its way going downward, it takes exactly the same amount of time as it goes upward. So you can notice that when it goes up and down, the velocity has only switched the direction. The magnitude of the velocity has not changed at all. So that's why the amount of time taken to go upward is the same as the amount of time taken to go downward. And remember that when acceleration is in the same direction as the velocity, then this object is going faster. And if the acceleration in the opposite direction of the velocity, then this object is slowing down. It goes slower. And also remember that speeding up and slowing down is not the same term. It's not an alternative to accelerating or decelerating. So speed up and slow down is referring to the speed only or the magnitude of the velocity, while accelerating and decelerating means the velocity is increasing or decreasing. Okay, so for example, so an object might be speeding up while it is actually decelerating. So let's say an object is moving in the opposite direction or in the negative direction. And its speed is increasing. Okay, so obviously its speed is increasing, it's speeding up, but when it comes to acceleration, it's a negative acceleration. Its initial velocity is, let's say, 0 meters per second, and its final velocity is negative 10 meters per second. So its velocity, the number itself is decreasing, going from 0 to a negative value. So that's what I call by the negative acceleration. Or an object might be slowing down but accelerating. So this usually occurs when an object is moving in the negative direction. Okay, so again, it's moving in the negative direction and its speed is gradually decreasing. And then finally it comes to a stop. So let's say its speed has, its velocity has changed from negative 5 meters per second to 0 meters per second. Then the velocity itself is increasing from a negative value to zero. So according to the formula of the acceleration, delta v divided by t, delta v is 0 minus negative 5, which is positive 5 meters per second. So it's the velocity is increasing, so acceleration is positive. So up until now, I was only dealing with the linear motion, which means an object is moving on a horizontal surface or moving up and down only. And now let's talk about the two-dimensional motion. So when an object moves on a surface. So the best example for two-dimensional motion in kinematics is the projectile motion. So projectile motion is actually one type of free fall, which means that object is moving in air under the influence of the gravitational acceleration only, without any of the air resistance. But as for the linear motion, the initial velocity is either zero, or its velocity is in the same direction or the opposite direction of the acceleration. While in the projectile motion, its initial velocity is not in the same direction as the vertical line, or the gravitational acceleration. So its velocity changes. So its velocity is changing the direction, and it's also changing the magnitude. So it's gradually pointing toward horizontal, and then it becomes horizontal at the maximum point, and then it gradually points downward. So this is a representation of the projectile motion and how its velocity changes at different position. So velocity is a vector quantity, and as for the vector, we can always separate it into the x component and then the y component. So for the initial velocity, I'm going to rewrite it as the addition of the two vectors, vx and then vy. So two of the components. And then along this projectile motion, only the gravitational acceleration is applied on this object. So from the very beginning to the end, it's always the gravitational acceleration that is pointing downward, which means only the vertical component of the velocity changes. So vertical component of the velocity is gradually decreasing. And then at the maximum point, the vertical component of the velocity is equal to 0, and then gradually the vertical component of the velocity becomes negative, pointing downward. On the other hand, Vx, the horizontal component of the velocity, is not changing along the whole the motion. And this is because there is no acceleration along the horizontal axis. So in the projectile motion, what we need to pay attention to is only the y component, so Vy, only Vy changes due to the gravitational acceleration, which is along the vertical line. And Vx never changes. So this explains why the path of the projectile motion is parabola, because Vx is not changing while Vy is always decreasing. So that's why it is, when it goes up, the next moment it's slightly pointing toward a horizontal, and next it's more horizontal, and next it's more flat, and then now it's pointing down, and more down. Okay, so sometimes it might not look like a projectile motion at first, but actually they are. So for example, when you throw a ball in a horizontal direction on a cliff, so its initial velocity is pointing in the horizontal direction. So next moment, due to the vertically downward gravitational acceleration, its velocity points down, and then the next moment it's pointing more downward, and the next it's pointing more downward. And next it's pointing more downward. Okay, so again, it's Vx is not changing during the whole process because there is no acceleration along the horizontal axis, but the Vy is always changing. So at the very beginning, Vy is equal to 0 because the velocity is just in horizontal direction. Next moment, Vy is pointing downward, but the magnitude is small. And then the next moment, Vy is pointing down, and then the magnitude is larger. Next moment, it's pointing down, and then the magnitude got even larger and larger. So now it's obvious that only Vy decreases while Vx is always constant. So no matter which one it is, this one or this one, they both represent a projectile motion. Okay, now let's try to use the equation. So there are only 3 equations that you need to know, and then they are all shown on the equation sheet. So 3 equations that we need to know are V final is equal to V initial plus the acceleration times t. The second one is x final, the final position is equal to initial position plus V initial t plus 1/2 at squared. And then the last one is V final squared is equal to V initial squared plus 2 times a times the change in the position or the displacement. Okay, so these 3 are in the equation sheet. And I'm going to add one more. So all of these, remember that all of these 3 equations are based on the condition that acceleration is constant during the whole process of the motion. And when I say acceleration is constant, it doesn't just mean the magnitude is constant. It also means the direction of the acceleration is constant. So for example, if the acceleration magnitude is the same, but it's changing the direction, then this is not constant acceleration. Constant acceleration means both the magnitude and direction are constant. Okay, so given this condition, I can add one more equation. So sometimes I can use the 4th equation to make the calculation faster. The last one is the change in the position or displacement is equal to 1/2 of the initial velocity plus final velocity. So this part actually represents the average velocity. Average velocity multiplied by time is equal to the change in the displacement. And I can use the velocity versus time graph to represent it. So assuming that this is a constant acceleration and assuming that this is a positive acceleration, so velocity increasing, then velocity versus time graph is a linear line because on the velocity time graph, the slope represents the acceleration. Constant acceleration means it's a linear line. And then remember that the area under the graph represents the change in the position or displacement. And this point represents the initial velocity, so when time is equal to 0. And this point represents the final velocity. Okay, so obviously this is a trapezoid, and then how I find the area of a trapezoid is 1/2 times a plus b multiplied by the height h. Okay, 1/2 times the upper base and then the bottom base, and then multiply by the height h. So A is represented by this part, B is represented by this part. So now I can just plug in V initial and V final. Then I get 1/2 times V initial plus V final multiplied by the height, which is time t. So this is how you get the very last equation, the 4th equation. Now, let's try to use this equation and then all of this graph to apply them to actual AP-style questions. So in this question, initial velocity is given, even though it's not explicitly stated. It says the ball is released from rest, which means its initial velocity is equal to 0. And then 1 second represent the time, and then the 1 floor has fallen 1 floor. Okay, so even though this is not stated in terms of the meters or the feet or inches, but because each of the floor is evenly spaced, so 1 floor actually represent the displacement, the amount of distance that it has traveled or the change in the position. So I'm going to use delta y to represent it. Then in the given, combining all of these 3 sentences. Okay, and one more thing, one more hidden information here is this is a free fall because it says the ball is just released. So as for the free fall, acceleration is always equal to the gravitational acceleration, which is 9.8 meters per second squared, pointing downward. So now I have acceleration, initial velocity, time, and the change in the displacement. Then combining all of these four, again, initial velocity, time, acceleration, and then the change in the position or displacement. Okay, so I know I'm not going to use equation 1 because final velocity is not given. So again, V final is not given, so I cannot use equation 3, and then I cannot use the fourth equation because final velocity is not given. So the only equation that I can use is equation 2. So I'm just going to replace x with y. Then I get this formula of delta y, change in the position or displacement, is equal to V initial t times 1/2 at squared, or 1 floor is equal to initial velocity 0 plus 1/2 times g times 1 second squared, where 1 floor is equal to 1/2 g. Okay, and it says it's asking us to find the number of the floors. So delta y, it's asking us to find the displacement when the ball has fallen like 3 seconds. Now I'm going to use exactly the same formula, but now delta y is a different displacement. Delta y prime is equal to V initial t prime plus 1/2 at squared. So the new change in the position, or the new displacement, is equal to 0 plus 1/2 g times 3 seconds squared. So that is 9 times 1/2 g. So it's 9 times of the amount of the displacement that has traveled in 1 second, which is 9 floors. It has traveled 9 floors. So the answer is C. It's between 7 to 10 floors. Question number 2. A student wants to investigate the motion of a ball by conducting 2 different experiments. And the student released the ball from rest and used a slow motion camera to film the ball as it falls to the ground. Okay, so in experiment 1, this is just a linear line motion, a free fall. It just released from rest, so it goes to vertically down. And then in experiment 2, the student horizontally rolls the same ball off a table and used the video analysis to plot the ball's horizontal position X and vertical position Y. Okay, so in experiment 2, the ball starts at a horizontal velocity, so it's going to follow this parabolic curve. It's going to follow the parabola, and then it is doing the projectile motion. So this is the initial velocity, and this is how its velocity changes over time. The graph from each experiment are shown. 2. Which of the following conclusions can the student draw from the graphs and why? Okay, so now when I compare the experiment 1 and 2, they have exactly the same y versus t graph. So their vertical position is changing at the same rate. The only difference is the horizontal position. So for experiment 1, its horizontal position is not changing at all because it's just moving up and down along the vertical line. In figure 2, in experiment 2, it started in a horizontal direction. So its horizontal position is also changing, but at a constant rate. This is a linear line, so its slope is represents the acceleration. It's a linear line, so its slope represents the velocity, and then the velocity is constant. The horizontally rolled ball travels a greater horizontal distance and takes a longer amount of time to reach the ground. Okay, so the first half is correct. It travels a greater horizontal distance, right? But it does not take a longer amount to reach to the ground. So no matter which one you pick, it's going to take exactly the same amount of time, because the amount of time taken to reach the ground is it depends on its initial vertical velocity, and then the vertical displacement, and then the vertical acceleration. And experiment 1 and 2 have exactly the same vertical components. They have traveled the same vertical displacement. Their initial vertical velocity are exactly the same. Both have initial vertical velocity of 0, and then both of them are experiencing the same vertical acceleration of 9.8 meters per second squared. So the second part is not correct. It's the same amount of time. So A is not true. B, the released ball travels with a slower speed and takes a longer amount of time to reach the ground. Okay, so again, not longer amount of time. It's the same amount of time. And C, since balls have zero horizontal acceleration, they reach the ground at the same time. And D, since the balls have the same vertical position at any given time, they reach the ground at the same time. So out of C and D, D is the right one. So C is actually true. They have the zero horizontal acceleration. Yes, it's true that both of them have zero horizontal acceleration. So in experiment 2, the ball is doing a constant horizontal motion, while in experiment 1, it's just not moving in horizontal direction. But it does not give us any information regarding the time taken to reach the ground. So we need to take a look at the vertical components. And when we take a look at the vertical graph, the vertical position versus time graph, at every single moment, they are at the same position, the same vertical position. So this explains why they will spend the same amount of time to drop to the bottom. 3. In experiment 1, what is the speed of the ball the instant it makes contact with the ground? Okay, so in experiment 1, so how we calculate or how we figure out the velocity is by drawing a tangent line on the position versus time graph, and then find the slope of that tangent line. So it's going to be this linear line. This linear line is tangent to the graph. And then its slope is a negative value, which means it's moving downward. And then how I'm gonna calculate the slope is by picking any of the 2 points on this slope. So approximately, so I can pick these 2 points. I can pick this point and this point. So approximately, its slope at when it has reached the ground is going to be delta V divided by is going to be 0 minus 1.6 divided by 0.55 minus 0.25. So negative 1.6 divided by 0.3. So that's approximately negative 5 meters per second. So as for the speed only takes the actual value. So if the velocity is negative 5 meters per second, then its speed is approximately 5 meters per second. Question number 4, suppose that experiment 1 and 2 are conducted at the same time. One student drops the ball from rest at the same instant that a second student horizontally rolls an identical off the table. After both balls have traveled half their vertical distance to the floor, what is the acceleration of the center of mass of the two ball system relative to the Earth? Okay, so now let's talk about what it means by the center of the mass and how we calculate the center of mass of the two ball system. So the center of mass is usually used to represent where the mass is, how the mass is distributed within an object. So not all the object has a regular shape, like a circle or a square. So most of the object in real world has irregular shape. So let's say for like human beings, the center of the mass is more toward the upper body. It's closer to the upper body because the skull is pretty heavy. It occupies a great percentage, a large percentage in the human body weight. So compared to the lower body, the upper body is heavier. The center of mass is a little bit above your belly button. And for irregular shaped object, the center of mass is more toward the part where more of the mass is concentrated. So, for example, if you have a stick like this, if one side is thicker and the other side is skinnier, and given that the density is the same, then the center of the mass is more on the left side of this stick. So this is for one single object, but in AP Physics 1, you barely get tested on finding the center of the mass within an object. We usually assume that that's just the center of the circle or the center of this like rectangular object. But you will be tested on center of the mass of the multiple object or the two objects. So let's say when you have two objects, So I'm going to use two rectangles to represent it. And then one of the rectangle has the mass of 10 kilograms. The other one has the mass of 20 kilograms. And then they are, let's say, 1 meters apart. Then how I calculate their center of mass is I'm going to use this formula of x center of mass is equal to x1 times mass 1 plus x2 times mass 2 divided by the sum of the mass, the total mass. So x1 and x2 represent the position of the center of mass for each of the object. So I'm gonna draw this reference frame, and then let's say this represents 0, and then this represents 1 meters. Then the position of the 10 kilogram object is 0, the position of the 20 kilogram object is 1 meter. And now I just plug in these numbers in the formula. Then x1, the position of the mass 1 times 10 kilogram, plus x2, 1 meters, the position of the mass 2, multiplied by its mass, and then divided by the total mass of 10 kilogram plus 20 kilogram. Then it is 20 divided by 30, so 2/3, approximately 0.67 meters. It means on this reference frame, 0.67 meters. So here, so this represents, so this 0.67 meters, this is the position of the center of mass of this two object system. And when you're asked to find the velocity of the center of mass, you are going to use the same method. The velocity of the center of mass is equal to velocity of each of the mass multiplied by its mass, and then you are going to add up the products and then divide it by the total mass. So going back to that question, okay, so in experiment 1, the ball is moving straight down. In object 2, the ball is moving along, doing a projectile motion, moving along the parabola, and then they have exactly the same vertical position. The only difference is the horizontal position. Okay, then it's acceleration of the center of the mass relative to the Earth. Okay, so when it comes to acceleration is a vector quantity. So we can calculate the horizontal acceleration and then calculate the vertical acceleration and then add them up together. So when it comes to the vertical acceleration, since both of them are moving down at the same velocity and then the same acceleration, so for both of them, AY, the vertical acceleration is G, just gravitational acceleration. On the other hand, for the horizontal acceleration, okay, so one is not moving horizontally, the other one is moving at a constant velocity horizontally. Then the velocity of the center of mass in horizontal component is equal to Vx of one of the ball multiplied by Vx of another ball. Okay, so in experiment 1, the ball is not moving at all in horizontal direction, so its horizontal velocity is always 0. So and then I'm going to divide it by the total mass, so m plus m. So eventually this is 1/2 of the horizontal velocity of the ball in experiment 2. So it means this is a constant velocity. And as for the constant velocity, acceleration is equal to 0 because acceleration is change in velocity over time. So this is 0 meters per second squared. Okay, so in horizontal direction, acceleration is 0. In vertical direction, acceleration is g. So when I combine them together, so this is AY. And this is AX. And since AX is 0, so when you add them up together, the acceleration is still equal to AY only. Next, question number 5. A student is provided with a battery-powered toy that the manufacturer claims will always operate at a constant speed. The student must design an experiment in order to test the validity of the claim. So when it comes to measuring the velocity or the position or acceleration of a moving object, we use either the photo gate or the motion detector. So I know for sure that um, which of the following measuring tools can the student use to test the validity of the claim? Select two answers. Okay, so uh, I know D is not right, a mass balance. So measuring the mass has nothing to do with its position or velocity or acceleration. So photogate and motion detector are used pretty often when it comes to measuring the velocity or the position or acceleration of a moving object. But remember that no matter which one you use, either the photogate or the motion detector, you always have to put it along the track where this object is moving. So the object is moving in the horizontal direction, then you will have to put the photogate along this horizontal track, either here or here or here. And it's the same for the motion detector. If you place it in the vertical in a vertical position compared to the its moving track, then it's not going to measure the position or the velocity. So oriented perpendicular is not correct for sure. So the answer is A and B. The photogate placed at the beginning and then the end, and then along the various location along the track. And B, a meter stick to measure the distance of the track that the car travels on. And the next question, do students want to determine the speed at which a ball was released when thrown vertically upward into the air? So the ball is released, but it's thrown vertically upward. So its initial velocity is pointing upward, and then its velocity gradually decreases until it comes to a stop, and then it starts to move down until it hits the ground. One student throws the ball into the air, while one other students measure the total time that the ball is in the air. Okay, the total amount of time starting from this to this. The student used a meter stick to measure the release height of the ball. So the release height of the ball. Okay, so given the release height, I can calculate the change in the position or the displacement delta y, which is the final position minus the initial position. So that's going to be negative of the release height, negative h. And then given the time, okay, so it's asking us to find the speed, its initial speed. And then this is a free fall. So of course we assume that acceleration is the gravitational acceleration pointing downward. So we're given one, two, three information, and then you're required to find the last one. Okay, then obviously C and D does not apply because the final velocity is not even given. So I cannot use C or D to figure out the initial. So not C or D. So it must be either A or B. And then it's from the moment in time in which the ball was released to the moment in time in which the ball reaches the highest point or until it hits ground. Okay, so the amount of time it measures is from initial all the way to it's going back, it hits the ground. So I will have to choose B. 7. An object undergoes an acceleration as it travels along a straight horizontal section of a track. Which of the following graphs could represent the motion of the object? Select two answers. So A, speed versus time graph. So usually in the velocity versus time graph, the slope of the line represents the acceleration. So this means it is a constant positive acceleration. So A is the right answer, and B, position versus time graph. On the position versus time graph, the slope represents the velocity. So it just means it's a constant positive velocity, so not B. And C, position and time squared. Okay, and D is velocity versus time. So I know D is not the right answer for sure because this is constant velocity. Or when I'm taking a look at the slope, which is 0, slope of the velocity time graph represent acceleration. So the right answer is A and C. So for the position versus time squared graph, if I convert it into the regular position versus time graph, then it's going to be a curved line. So it means that it has a different tangent line. It has the tangent line of different slopes and different time, which means the velocity is constantly changing. Question number 8. A monitor sensor is used to create the graph of a student's horizontal velocity as a function of time as the student moves toward and away from the sensor. The positive direction is defined as the direction away from the sensor. Which of the following describes the student's final position x final in relation to the starting position x0 and the student's average horizontal acceleration ax between 0.0 and 3.0 seconds? Okay, so first off, this is a velocity versus time graph. So the area under the graph represents the change in position or the displacement. So this is a starting position, and this is where the final position must be. So if I add up, if I calculate the area under the graph, then obviously the positive part is greater than the negative part. So delta x is going to be greater than 0, which means x final minus x initial is greater than 0. So x final is greater than x initial, which means the final position is more away from the monitor sensor. So either A or B. And then when we calculate the acceleration ax between 0 and 3 seconds, okay, 0 and 3 seconds. So when it comes to the horizontal acceleration, so how we calculate the average acceleration is by calculating delta v divided by delta t. Okay, and then at position 0, 0, its velocity is represented by this slope. Okay, so this slope is this is a positive slope, which means v initial is positive value, and then this represents a so at time t is equal to 0, when time t is equal to 3, so this represents the velocity at 3 seconds. So v final is equal to 0. Okay, so delta v is v final minus v initial. So it is 0 minus a positive value divided by t. So it must be a negative acceleration. So B is the right answer. A car initially at rest accelerates at 10 meters per second squared. The car's speed after it has traveled 25 meters is most nearly. So initially at rest means its initial velocity is equal to 0 and its acceleration is 10 meters per second squared. So after it has traveled 25 meters, which means its final position is 25 meters, assuming that its initial position is 0 meters. Then, okay, so now I have these informations. So out of these three equations, I need to find the equation that has initial velocity, final velocity, acceleration, and the displacement. So the right one is equation 3. Equation 3 is the only one that contains all of these four information. So v final squared is equal to v initial squared plus 2 times acceleration times the displacement. So 0 squared plus 2 times 10 times 25. So that is 500. So v final is square root of 500, or approximately like 20 something. So it must be 22. So I know it's not 25 because 25 squared is 625, so that's way too big. But I know it's going to be greater than 20 because 20 squared is 400. So it's between 20 and 25. Question number 11. A student performs an experiment in which the horizontal position of a toy car is recorded on ticket tape from a device that places dots on the tape at equal time intervals. So in between the dots, consecutive dots, it represents the same time interval. So the farther the dots are away from each other, which means the speed is greater, and then when the dots are closer to each other, it means the speed is smaller. The series of the dots in the figure represent the motion of an object moving from the negative direction to the positive direction along the horizontal direction. The time interval between each recorded dot is 1 second. Which of the following experiments could the students have conducted to create the data shown on the ticket tape? A. The toy car initially increased the speed. Okay, so in between the dots, the distance is getting greater and greater and greater, and then it starts decreasing again. So it has speed up and then slow down. It has speed up, travels at a constant speed, and then slow down. So the right answer is B. It increased the speed, travels at a constant speed, and then decreased the speed. Student wants to launch a toy dart toward a target that hangs from a light string. At time t is equal to 0, the dart is launched with an initial speed of v0 at an angle theta above the horizontal ground. At the instant the dart is launched, the string is cut such that the target begins to fall straight down. The positive horizontal direction is considered to be to the right, and the positive vertical direction is considered to be up. A student makes the necessary measurements to create the graph shown, which represent the vertical component of the velocity as a function of time for the dart and for the target from t is equal to 0. This is for the dart, this is for the target. Until instant the dart hits the target. Okay, dart hits the target. Okay. At time t is equal to 0, the target is vertical distance h above the dart. The curves for the dart and target each have the same area between them and horizontal axis. Both curves also have the same slope. Which of the following is the best method to determine the distance h from the graph? Okay, so h is the distance between the target and the vertical distance between the target and the dart. And as for the vertical velocity, so this amount of area represents the displacement, the vertical displacement. So y, delta y, when it comes to the target, when it has hit the dart. And then this area represents the delta y for the dart when it hits the target. Okay, so when they meet each other, so let's say the target is here and then the dart is here. Okay, so this is delta y target and this is delta y dart. Okay, so of course one is positive and the other one is negative, but when we take the absolute value for both of them, then they add up to the total height of h, the vertical height between the target and dart at the beginning. So I just need to add up these two areas and then taking positive for both of them. So it will be the area between the dart line and then the target line. That is the area under the curve for the darts data. Okay, not A. So B, find the twice the area under the curve for the darts data. Okay, so it has stated that the area below these two curves are exactly the same. It's just that one is positive, the other one is negative. So by calculating the dart area and multiplying it by 2, that is the area between these two lines. 13. Which of the following graphs could represent the vertical component of the velocity as a function of time? For the dart and target immediately after the dart is launched, and then the target begins fall. Okay, so immediately after the target, okay, so the vertical component of the velocity. So the target is going downward, which means its velocity, vertical velocity is negative, while dart is going upward. So its initial velocity must be positive. So for the target, it's going from 0, because it was at rest, to negative value. Okay, and then on the other hand, for the dart, its vertical velocity is given. So it goes from positive and then it gradually decreases. So D is the right answer. And question number 14. So figure 1 shows a displacement versus time graph for the dart, and figure 2 shows a displacement versus time graph for the target. Okay, so this is for the target, this is for the dart. One is increasing from 0 to a positive value, the other one is decreasing from positive. Which displacement component, horizontal or vertical, is represented by the graph for each object? Okay, so either for dart or for target, they're actually both doing a free fall motion, which means they're moving under the influence of the gravitation or acceleration only, without any of the air resistance. So their horizontal component must have a zero acceleration. So for the dart, its horizontal velocity should keep the same. So the dart is going this way. So the dart is going along this curved line. It's doing a projectile motion, but its horizontal component of the velocity should always be the same. Well, its horizontal displacement must be just a linear line increasing. And on the other hand, its vertical component follows the acceleration graph. On the other hand, its vertical component is gradually increasing, but at a decreasing rate due to the acceleration pointing downward. So this explains why at the very beginning it has a very steep tangent curve, but gradually its tangent line is getting flatter and flatter, and then at the very end its tangent line becomes horizontal, which means its velocity is zero. And this refers to the vertical velocity, not the horizontal velocity. So it represents the vertical displacement. So for both of them, it represents vertical. So the answer is D. Next is question number 15. A student drops a rock from the top of a cliff such that the rock falls downward toward the Earth's surface in an absence of the air resistance, aka this is free fall. The downward direction is considered to be positive direction. Okay, so when it goes down, the velocity is positive. The graph shows the rock's velocity as a function of time. Which of the following methods should be used to determine the total distance traveled by the rock after 4 seconds? Okay, so within the first 4 seconds, okay, so this is a velocity versus time graph, and then we usually use the area under the curve to represent the displacement, and then it has traveled. So from 0 to 4, it's going to be the area of this right triangle. 1/2 times 4 times like 40, the answer should be 80 meters. So out of A, B, C, D, the answer is B. Use the area under the curve as it sees the rock traveled 80 meters in total. Next, question number 16. An object travels along a straight line across a horizontal surface. And its motion is described by the velocity versus time graph shown in the figure. Which of the following methods will determine the total displacement of the object between 0 and 5 seconds? Again, velocity versus time graph, and it's moving only along the horizontal surface. So it's going to be the area under this horizontal velocity versus time graph. So that is, okay, A, finding a slope, that's not right. B, dividing the change in the velocity by the changing in time. No, that's acceleration. C, finding the area bound by the horizontal axis and the curve from 0 to 5 seconds. So C is the right answer. And D, using average speed is equal to total distance divided by the total time, and then multiply the average speed by 5 meters per second by the average speed of 5 meters per second by a total time of 5 seconds. So D is actually applying the force equation. So it states that the change in the position or displacement is equal to 1/2 of the V initial plus V final. So the average speed, assuming that the acceleration constant, multiplied by the time. So D is also right. So C and D are both correct answers. Question number 17. A student wants to study the motion of an object that has a constant acceleration. Which of the following experiments could a student conduct to provide the best situations in which an object has a constant acceleration? Select 2 answers. A constant acceleration, and okay, which of the following experiment could a student conduct to provide a best situation in which an object has a constant acceleration? Select 2 answers. A, release a ball from rest near Earth's surface. So this is actually one of the best situations that describes a constant acceleration, because as an object goes through free fall, it only experiences the gravitational acceleration, which is pointing downward. So A is correct. B, release a toy car from rest such that it travels along a different looped sections of a track. Okay, so when it travels along a different loop section, it's not experiencing a constant acceleration. So that's not B. C. Launch a water-propelled rocket from rest such that it travels into the air and falls back to the Earth's surface. So it travels into the air and launches back. So C actually represents a projectile motion. And D release a cart from rest such that it travels down an incline of 40 degrees with respect to ground. Okay, so both C and D actually represents the constant acceleration. So C represents the projectile motion of an object, but because its velocity is not pointing in the same direction as acceleration. So I would say D is a better situation that describes an object with a constant acceleration. So in D, when a cart is moving downward, its speed is getting faster and faster because it experiences an acceleration pointing down along a slope. Question number 19. An object is released from rest near a planet's surface. A graph of the acceleration as a function of time for the object is shown for the 4 seconds after the object is released. So acceleration has always been a negative constant. The positive direction is considered to be upward. What is the displacement of the object after 2 seconds? Okay, so since acceleration is a constant value, negative 5 meters per second squared, and then the time is 2. Time is equal to 2 seconds. Okay, then given that V final an ob Next, question number 19. An object is released from rest near a planet's surface. The graph of the acceleration as a function of time is shown for 4 seconds after the object is released. The positive direction is considered to be upward. What is the displacement of the object after 2 seconds? So it states that object is released from rest, which means its initial velocity is equal to 0. And then its acceleration is a constant value of negative 5 meters per second squared. The time is 2 seconds. So given initial velocity, acceleration, and time, we need to find the displacement. Okay, so displacement delta x is equal to v initial times t plus 1/2 at squared. So I can plug in all the values. Then it's 0 plus 1/2 times negative 5 meters per second squared multiplied by 2 seconds squared. So that is negative 10 meters. The answer is B. And next, question number 20. So an object is sliding to the right along a straight line on a horizontal surface. The graph shows the object's velocity as a function of time. What is the object's displacement during the time depicted in the graph? Okay, so again, the displacement is represented by the area under the velocity time graph. And remember that if it's above the x-axis, then it's positive. If it's below the axis, then it is the negative. For this is a linear velocity line, and then these two triangles are exactly the same. They're congruent to each other. The only difference is one is positive, the other one is negative. So they add up to 0. And question number 21, a bowling pin is thrown vertically upward such that it rotates as it moves through the air. Initially, the center of the mass of the bowling pin is moving upward with a speed of v initial of 10 meters per second. The maximum height of the center of the mass of the bowling point is most nearly. Okay, so this is a typical free fall motion. So as for the free fall motion, given that its initial velocity, then due to the downward acceleration, its velocity gradually decreases until it reaches 0, until it temporarily comes to a stop. Then the change in the position or the displacement is equal to v initial times t plus 1/2 a t squared. So acceleration is pointing downward, so it's negative g, assuming that upward is a positive direction. then delta y is equal to okay, so only acceleration, initial velocity, and final velocity are given. So combining these three, when initial velocity, final velocity, and acceleration is given, I need to figure out the maximum height, so the vertical component of the position or the displacement. Okay. Then I'm gonna cross out equation 1 because I am then I'm going to cross out equation 1 because time is not the subject of interest. I am interested in the delta y. And then again, I'm going to cross out equation 2 because again, time is not the subject of interest. So I'm going to choose equation 3, which states that v final squared is equal to v initial squared plus 2 times a times delta y. So 0 is equal to v initial squared plus 2 times negative g multiplied by the height h. Then v initial squared is equal to 2gh. Then h is equal to v initial squared divided by 2g, which is a. Question number 22. At time t is equal to 0, a moving cart on a horizontal track is at position 0.5 meters. Using a motion detector, students generate a graph of the cart's velocity as a function of time. At time t is equal to 2.5 seconds, the cart's position is most nearly. Okay, so the final position, it's asking for the final position. And the final position minus initial position is equal to the displacement. So final position is equal to initial position plus the displacement. So initial position 0.5 plus the displacement. And displacement is represented as the area below the curve, the velocity versus time graph. And this is between 0 and 2.5 seconds. These two parts are exactly the same. These two triangles are exactly the same. So they cancel out each other. I only need to calculate the area between 0 and 0.5 seconds, this area. And then that area is equal to 1/2 times the upper base plus the bottom base. So 1/2 times 2 plus 3 multiplied by the height is 0.5. So that is 0.5 plus 5 divided by 4, or 1.25. So it's 1.75 meters. The next, two blocks are tied together with a string. They are thrown onto a layer of ice such that they spin around their center of mass C as they slide horizontally across the icy surface. A graph of the two block system's velocity as a function of time is shown. Based on the graph, which of the following claims are correct about the system? So when it's a system, it's taking these two objects as one single system. So what really matters here is the center of the mass. Okay, and the direction of that. So they are spinning, and then it's moving to the right at the same time. And this shows the system's center of mass velocity. So its velocity is gradually decreasing. The total displacement of an individual block is 0 because it travels in a perfect circle around the center of the mass of the system. So that's not 0 because while it's spinning around, it's also moving toward the right. So it's moving along this track. So its displacement is not going to be 0. B, the acceleration of the center of the mass of the system is constant. So B is actually correct. So according to this center of mass velocity versus time graph, the velocity decreased at a constant rate. So its slope is a constant value. It's a negative constant. So B is correct. C, the change in the velocity per unit of time for the system center of mass changes as time increases. Okay, so again, the change in the velocity per unit of time, it represents acceleration. And acceleration is constant. It does not change. And D, the system's acceleration vector is opposite to the direction of the system's velocity vector. That is correct. So when acceleration and the velocity vector are pointing toward the opposite direction, then velocity is actually the velocity is decreasing. So velocity is a positive value. So while it's moving toward the right, if the acceleration is a negative value, then at the next moment, the velocity will gradually decrease. So B and D are the right answer.